All right, welcome to the second semester of organic chemistry. What I want to do before we get into new material is spend a couple of lectures reviewing stuff that you should remember from the first semester. I'm going to go through some stuff really quickly. I'm going to start from the basics and get to the end of the semester in two lectures. This one covering the structure of organic molecules and the next one covering the reactions that you learned last semester of organic molecules. I'm going to go through a lot of material very quickly. Don't worry, the rest of the semester won't be quite this quick, because hopefully this is all review. If there are areas where you feel rusty, these are things that are important that you should go back and look at. Come to me in office hours if you have any further questions about any of these things. I want to make sure that we're all starting this semester kind of with the same at least key points of understanding. All right, let's start from the very basics. You know that an atom is made up of three fundamental particles. Protons are positively charged, they have a mass of 1 atomic mass unit, and they're found in the nucleus. Neutrons have 0 charge, they're neutral. They also have a mass of 1 atomic mass unit, and they're also found in the nucleus. Electrons are negatively charged. They have almost 0 mass. They move very quickly relative to the protons and neutrons, and they are found somewhere outside of the nucleus. More on that in a moment. An element is defined by the number of protons in the nucleus. So for instance, here I show carbon. The atomic symbol, by the way, is a 1 or 2 letter code for an element. Usually it has the first letter of that element, except, there's only 26 letters of the alphabet, and there's, over 100 elements, so we have to have a couple 2-letter codes, etc., to help get all of them in, like, for instance, Ca for calcium and Cr for chromium, etc. But there's the atomic symbol, and all carbons have 6 protons in the nucleus. Everything with 6 protons in the nucleus is carbon, so these are identical to each other. That number 6 is called the atomic number, and we'll sometimes write that as a subscripted number down and to the left of the atomic symbol. Superscripted to the left is a number called the mass number. The mass number is the total number of protons and neutrons in the nucleus. So since carbon, by definition, has 6 protons in the nucleus, if we had carbon-12, well, it's got 6 neutrons in the nucleus, because 6 plus 6 makes 12. Now, not all carbons have a mass number of 12. Some, for instance, have a mass number of 13. That is, they've got 6 protons, because all carbons have 6 protons, and they've got 7 neutrons in the nucleus. Carbon-12 and carbon-13 are called isotopes of each other. That is, the isotopes are atoms with the same atomic number, but different mass number. Isotopes have the same chemical properties, because that's based on the number of protons in the nucleus, but some of their properties are different, as we'll learn, for instance, when we talk about nuclear magnetic resonance spectroscopy later this term. There's a final number written here, this one superscripted to the right, and that's the charge. And the charge is the balance between positives and negatives. That is, it's the difference between the number of protons in the nucleus and electrons somewhere outside the nucleus. So if it's 0, they're the same. So this guy would have a total of 6 protons, 6 neutrons, which we got from the mass number here, and 6 electrons, because it has 6 negatives to balance out the 6 positives. If there was more electrons than protons, we'd have a negative charge here. If there was more protons than electrons, we'd have a positive charge here. Let's talk about those electrons. Here's a couple of pictures of the atom hydrogen. This is a Bohr model of a hydrogen atom. In the Bohr model, we have a nucleus in the middle, and we got the electrons moving around in a nice circular orbit outside the nucleus. That's good as far as it goes, but the Heisenberg uncertainty principle says that we can't nail down the electrons like that. Instead, we have to talk about electrons being in a region of probability, that is kind of a cloud of electron density, where the electrons are somewhere in a region, a three-dimensional region, which is called an orbital, which is a mathematically defined three-dimensional region that describes an area of probability where the electron might be. You recall from general chemistry that there are different types of orbitals. We talked about electron configuration. There's the energy levels. The closest in to the nucleus is the first energy level, then the second, then third, and the fourth, as you move further out from the nucleus in concentric spheres. The first energy level has only an s orbital. The second energy level has an s and 3 p's. The third energy level has an s, 3 p's, and 5 d's. The fourth has an s, 3 p's, 5 d's, and 4 f's, and 7 f's, etc. As you go out. Fortunately, in organic chemistry, we're only going to really worry about s's and p's. I might occasionally make a reference to d orbitals. I'm never going to refer to f orbitals after today. When you fill in electrons, the Aufbau process says that you start with the electrons closest into the nucleus, and then they move as you fill in more electrons. They get further and further out from the nucleus. It's like putting books on a shelf, and you start from the lowest shelf, and once the lowest shelf is filled, you go to the next shelf, and the next, and the next, and the next. If we look at here I show the electron configurations for some molecules, or sorry, some atoms. I go through like the first 12 and then I skip ahead a bit. We start seeing some patterns. We fill in the first energy level. It can only hold up to 2 electrons because it only has an s orbital, and each orbital can only hold up to 2 electrons. So hydrogen has 1 electron, that goes in the first s orbital. Helium has 2 electrons, they both end up in the 1s orbital. But lithium has 3 electrons, so 2 of them end up in the 1s orbital, but then that's full, and so the next electron has to go into the next energy level, etc. If we compare things in the periodic table that are in the same column, we start seeing some patterns. Things in the same column will always have the same pattern of valence electrons. The valence electrons are the electrons in the outermost energy level that has any electrons at all. So for instance, if we compared fluorine to chlorine to bromine, for fluorine, the valence electron is the second energy level. And the second energy level in fluorine has a total of 7 valence electrons, 2 in the s orbital and 5 in the p orbitals. Chlorine is the same, it's just the third energy level, but it's still the same pattern of 2 electrons in s orbital and 5 electrons in p orbitals. And bromine is the same. For bromine, the valence electron is the valence shell is the 4th energy level, and that again has 7 valence electrons. You recall that the periodic table is arranged where things in the same column have the same properties. So the properties, the chemical properties, the reactions these things do, is somehow related to the pattern of valence electrons. Another thing we notice is that the far right-hand column of the periodic table, the noble gases, helium, neon, argon, krypton, they all have full valence shells. Helium's kind of weird. Helium and hydrogen can only get up to 2 electrons around them, so that's a full valence shell for those guys. So helium's got a full valence shell, but neon, argon, krypton all have 8 electrons. And these guys are all unreactive. So there's something special about that noble gas arrangement. It's unreactive, and so if things have that arrangement, they'll be at their most stable form. That's called the octet rule. Atoms that aren't noble gases would like to get to the most stable arrangement. And they're going to do that by trying to achieve that octet. There's a couple of different strategies to get there. The first is called ionic bonding. When we have elements that have very different electronegativities, what's that? Let's define some terms here. Electronegativity is the attraction between the nucleus and the electrons. Things in the upper right-hand periodic table have a very high electronegativity, excluding the noble gases, and things in the lower left corner have the lowest electronegativity. You might remember this little mnemonic, Fonkelbrush. Fluorine, oxygen, nitrogen, etc. are the most electronegative elements. Fluorine and oxygen are probably the ones to really remember as being the most electronegative elements. Notice hydrogen has an electronegativity very similar to carbon. Okay, if we have two elements that have very different electronegativities, take sodium, which is on the far left-hand side of the periodic table, very low electronegativity. So that means it doesn't hold on very strongly to its electron, and it doesn't really want to grab other electrons. Whereas chlorine has a very high electronegativity. It wants to keep all the electrons it has, and it wants to grab others. They also both want to achieve a noble gas arrangement. Sodium could either gain 7 electrons, because sodium has an valence electron has an electron configuration of 1s2, 2s2, 2p6, 3s1. Now notice, if you added 7 electrons to that, you'd get 1s2, 2s2, 2p6, 3s2, 3p6. That would be a noble gas arrangement. But you could also get a noble gas arrangement if you lost 1 electron, because you'd go to 1s2, 2s2, 2p6, and that's it. That's a noble gas arrangement. So sodium is really willing to give up electrons, and if it gives up 1, it has a noble gas arrangement. Chlorine, on the other hand, has 7 valence electrons. It could get to a noble gas arrangement by giving up 7 or simply gaining 1. And chlorine has a very high electronegativity. It would rather gain than lose. So if sodium wants to give up an electron, and it has to go somewhere, electrons don't just disappear, well, chlorine wants to grab an electron. And it's perfect. Everybody's happy. Well, almost. Because they've got full octets, but once sodium, which is neutral, loses an electron, it becomes positively charged. And chlorine, once it gains an electron, we call that chloride, it becomes negatively charged. And there's a second aspect to stability. There's noble gas arrangement, but there's also a balance of charges. Things don't like to have an imbalance of charges, and so the solution, though, is once you've got this sodium plus and chloride minus, Coulombic attraction, that is the attractive force between oppositely charged species, will keep these guys close to each other. And that way, the pluses and minuses balance each other out. Okay, that's one way to achieve octets. But the other way, and the way that's more important for organic chemistry, is covalent bonding. In covalent bonding, you've got atoms with similar electronegativities. I like to compare these things to tug-of-wars. In ionic bonding, it's like you've got a tug-of-war between a really strong team and a really weak team. And the really strong team will simply pull the rope away from the really weak team. But in a tug-of-war between two equally matched teams, they'll both just keep pulling on the rope. And that's what happens in covalent bonding. Let's imagine bringing 2 hydrogens near each other. This hydrogen has 1 electron. It really wants 1 more, because for hydrogen, 2 electrons is a noble gas arrangement. The other hydrogen also wants 1 electron. But this guy and this guy have identical pulls on those electrons, so there's no way that the hydrogen on the left is going to pull the electron away from the hydrogen on the right, or vice versa. Instead, if they come near each other, near enough to each other, this hydrogen on the left will feel the effect of having 2 electrons near it. And that'll be a noble gas arrangement, which will make that hydrogen feel fine. The hydrogen on the right also feels the effect of 2 electrons near it. Again, getting an effective noble gas arrangement around that hydrogen. As long as these 2 hydrogens stay close enough to each other, they will both feel the effect of having noble gas arrangements. And so that will hold these 2 hydrogens near to each other. That's called a covalent bond. Notice the name has co, with, together, like cooperate, and valency as part of the name. They're sharing a valency, as it were. Finally, we should note that some bonds are, these are the extremes. Completely stealing versus completely sharing. A lot of things are in between. And we call those polar covalent. That's where there's an uneven sharing, like say a hydrogen-oxygen bond. It's a covalent bond, but the electrons are closer to the oxygen than they are near the hydrogen. or you could think of them as spending more time near the oxygen than they do near the hydrogen. And therefore there's an imbalance of charge, a slight imbalance of charge. So we get a partial minus and a partial positive end. Okay, once we had covalent bonding, then we moved on to talk about Lewis structure. In Lewis structure, we considered how we could take a series of atoms and all of their valence electrons and put them together in an arrangement to give a stable overall structure. The stability comes from having full octets and the best possible balance of charges. This could involve shared pairs, which are bonds. It could also involve double bonds, which is 2 shared pairs, or triple bonds, which are 3 shared pairs. We also see lone pairs, which are unshared pairs. It's key in Lewis structures to account for all of the valence electrons. And sometimes we also have to include a formal charge. A formal charge is a way of accounting for the overall location of charge. And you can get that by taking the number of electrons, number of valence electrons on a neutral atom, minus the number of bonds to that atom, minus the number of unshared electrons. Let's see this with these 3 molecules, CH4, methane, NH3, ammonia, and CO, carbon monoxide. Carbon starts out with 4 valence electrons, so if we had 1, 2, 3, 4, and each of our hydrogens has valence electrons of their own, so 1, 2, 3, 4. If we then started sharing an electron from carbon and an electron from hydrogen, bond. Electron from carbon, electron from hydrogen, bond, etc., all the way around. Now, all of our atoms, we've accounted for all of our valence electrons, because we got to account for 8 valence electrons, and everybody has a noble gas arrangement, because carbon has 8 electrons near it, and each of our 4 hydrogens has 2 electrons near it. Notice we're sharing electrons here. Also, we get formal charges of 0 on each of our atoms, because carbon starts out with 4 electrons, 4 minus 4 bonds, minus 0 unshared electrons on carbon is 0. 4 minus 4 minus 0. Each of our hydrogens also has a formal charge of 0, because 1 minus 0 equals 1. Or sorry, equals 0. So notice everybody's neutral and everybody has a noble gas arrangement. In ammonia, we also get noble gas arrangements, but here notice that nitrogen started out with 5 electrons, so we had 1, 2, 3, 4, 5, and each of our 3 hydrogens had 1. So we get noble gas arrangements where this nitrogen feels the effect of 3 shared pairs and 1 lone pair. Each of our hydrogens also has a noble gas arrangement. Each of our hydrogens, as in methane, has a formal charge of 0, and nitrogen also has a formal charge of 0, because 5 minus 3 minus 2, a neutral nitrogen atom has 5 valence electrons, minus 3 bonds minus 2 unshared electrons is 0. Finally, we have carbon monoxide. Here, the best arrangement turns out to be this, where we've got noble gas arrangements on carbon and oxygen by having a triple bond between the two and lone pairs on each end. Here, though, we get non-zero formal charges. Carbon, a neutral carbon atom, has 4 electrons, 4 valence electrons. So 4 minus 3 minus 2 is a negative 1. Oxygen starts out with 6 valence electrons, but 6 minus 3 minus 2 is plus 1. So notice here, we have noble gas arrangements, but we do have non-zero formal charges. So there's a negative end and a positive end to carbon monoxide. Now, when you're drawing Lewis structure, it turns out that just sometimes one Lewis structure is not enough. If I asked you to draw the structure of ozone, that is O3, you might come up with this structure, but your neighbor might come up with this structure. Now notice these are very similar to each other, but if we labeled the oxygens as, left, middle, and right, in this structure we have a double bond between left and middle and a single bond between middle and right, and we have a negative charge on the right-hand oxygen. In this structure, we see the double bond between middle and right and a negative charge on the left-hand oxygen. Now, it turns out that the difference between these two pictures has nothing to do with where the atoms are. They're in exactly the same arrangement, but it's just where the electrons are. But the electrons are moving at pretty much the speed of light, and so it's pretty much like they're just smeared out across, like sometimes they're here and sometimes they're there, but that's really not a good way to look at it. Really, the electrons are really just spread across this whole thing. The real thing is not this at times and this at other times. The real thing is actually an average of these structures, something like this, where we've got bonds that are somewhere between a single bond and a double bond, and we've got partial charges. This lowercase Greek delta means partial. Here's a electrostatic potential surface that shows sort of a charge distribution, and all you need to know here is that red is more negative and blue is more positive. The analogy I like to use for resonance is, imagine you're a knight in King Arthur's court, and you go to Africa, and you see a rhinoceros, and you come back to merry old England, and you tell Lancelot and Galahad and Percival or whoever about this rhinoceros. Now, they don't have any frame of reference to talk about rhinoceroses, because they've never seen a rhinoceros. Nobody had who lived in England, because people didn't travel. I don't know how you got there and back, but that's beside the point for our analogy. Well, you say to your friends, well, this beast I saw looked something like a unicorn and something like a dragon. That is, it had some of the properties of a unicorn. It had a horn on its nose. And it had some of the properties of a dragon. It was strong and it had a thick hide. And so your friends say, oh, I get it. It's something like a unicorn and something like a dragon. Now, key to this analogy is unicorns and dragons are fictions. But your friends have a mental picture of what at least they think unicorns and dragons look like. And they can take those mental pictures and sort of merge them to come up with the real thing. And that's what happens in resonance. Neither this picture nor this picture is a real thing. The real thing is an average of the two. But these pictures are fairly easy to understand because we know what single bonds and double bonds are. We know what a minus charge is and a plus charge is. A partial minus charge, that's not very clear. And a dotted line here representing somewhere between a single and a double bond, again, that's not very clear. But if I say the average of these two structures, that's much more clear. That's why we draw resonance. But the key to resonance, again, is it's not this or that, it's some average. Okay. Also, in the previous semester, we talked about the shapes of molecules. If we were dealing with transition metals, we might have to deal with some more complex shapes. But for us, the most complex thing we're going to have to deal with is up to 4 groups of electrons around a central atom. And the shape of these things is going to be driven by valence shell electron pair repulsion theory, VSEPR, or VSEPR, which is exactly what it sounds like. Valence shells, electron pairs, so that's bonds and lone pairs, repel each other because electrons are negatively charged and like charges repel. And so they want to get as far apart as possible. If I only had 2 bonds, well, the farthest apart possible I can get 2 bonds that are attached to a central atom is 180 degrees, a linear shape. If I had 3 bonds attached to a central atom, well, the best way to arrange 3 bonds to get them as far apart as possible is to divide the circle into thirds, 120 degrees, what's called a trigonal planar shape. If I had 4 bonds, well, if I stuck to 2 dimensions, I'd get 90 degrees. But if I twist those into 3 dimensions, I can get those bonds at 109.5 degrees away from each other. And that's the best arrangement of 4 bonds. If I have a combination of bonds and lone pairs, as shown in these other molecules like HNO, ammonia, and water, we still get arrangements that are 120 degrees and 109.5 degrees, or at least approximately those values. But when we describe the names of molecules, we only talk about where the actual atoms are, not where the electrons are. The electrons are like the wind, and the atoms are like the branches of the trees. You see where the branches of the trees are, but they're where they are because of the effect of the wind. But you don't actually see the wind. And so if you were to describe the shape that the tree was bent in because of the wind, you describe where the tree is. And so, for instance, we describe these as bent, trigonal, pyramidal, and also bent shapes. Again, there are more complex shapes for transition metals, but for organic chemistry, we're not going to worry about those. All right. We also talked about bonding. We didn't stay to just this Lewis structure picture for the same reason that we didn't stay with the Bohr model of the atom. Remember, the Bohr model of the atom recognized that we can't nail down electrons. Heisenberg uncertainty principle says that we can't simultaneously know the location and momentum of an electron. That's one way to describe Heisenberg. And so instead, with an atom, instead of having these nice neat orbitals, we described nice neat orbits, circular orbits, we described orbitals, that is, three-dimensional regions of probability. With molecules, we'll do the same thing. We'll call these molecular orbitals. So how can we get molecular orbitals? We get molecular orbitals by combining atomic orbitals. There's a couple of rules to learn about combining atomic orbitals. Well, there's like 3 rules to learn. First rule is the number of orbitals is conserved. So if we start with 2, we'll end with 2. If we start with 10, we'd end with 10, at all points in between. Second rule to learn is that when we combine orbitals, they can combine in constructive and destructive ways, that is, in phase and out of phase ways. So for instance, let's take 2 hydrogen atoms and let's bring them together to make H2. So here I show a hydrogen s orbital and a hydrogen s orbital. I could show that as kind of a 3-dimensional sphere, or I could take a slice through that sphere and say the orbital shape looks something like a bell curve, distributed into 3 dimensions, but let's just take this 2-dimensional slice as a bell curve. That has a phase. That phase might be, in this graph, might be either positive, or in this graph I show negative. If 2 things came together of the same phase, so if I brought 2 hydrogens together in the middle, as I bring these 2 hydrogens closer, this one and this one closer to each other, I'm getting combinations. I'll get to these combinations in a moment, but let's start with this one and this one. These 2 orbitals could come together in the same phase or in the opposite phase. If they're in the same phase, when we add these 2 waves together, they're going to add to each other. That's constructive overlap. That is, here in the middle, the sum of the red and the blue is they're both positive values. You're going to get a more positive value, a bigger positive number. On the other hand, when they're the opposite phase, here in the middle, right in the middle I've got some positive value for the blue and some negative value for the red. The sum of those is going to be 0. And so I'm going to have a point where this goes through 0. It changes from one phase, the green curve, which is the sum of the blue and the red curves, is going to go from positive to negative, and it's going to go through 0. That's what the orbital looks like. Now, this phase thing doesn't have a lot of physical reality except when we're combining orbitals, because the actual electron density is the square of this waveform. So the actual electron density is always non-negative. That is, it might be 0 or it's positive. Now here, if I look at the constructive overlap, where things were the same phase, notice this is all positive, and in the middle it's greater than either of the individual s orbitals. On the other hand, this out-of-phase combination, the electron density has a point of 0 electron density, because here the square of 0 is 0. That's called a node. Another way of putting it is just using shadings. If I bring together 2 things of the same shade, in the middle they add up. If they're the opposite, in the middle they cancel out. The other rule to learn about orbital combinations is in phase is always lower at energy, and out of phase is always higher in energy. So if I start with these two s orbitals and I bring them together to make two new things, which we're going to call sigma and sigma star, one's in phase, that's going to be lower, and one's out of phase, that's going to be higher. But now we have to put the electrons into this new set of orbitals. If I had two hydrogen atoms, I've got a total of 2 electrons to deal with. And I'm going to put those into this set of molecular orbitals in the same way that we put electrons into a set of atomic orbitals. That is, I'm going to start at the lowest energy orbital. And I'm going to fill that until that's full, and then the next electrons are going to go next, blah, blah, blah. That is, if I have a total of 2 electrons, they're going to both end up in this sigma orbital. So if I compared 2 hydrogens together, that is the molecule H2, to 2 hydrogens separately, if you look at the energy of the electrons, they end up in a lower energy arrangement as long as those 2 hydrogens stay close enough together that we can mix their orbitals. And that's ultimately what a covalent bond is. That's an orbital description of a covalent bonding. When you bring 2 atoms close to each other, their orbitals mix in such a way that the electrons end up in lower energy combination orbitals, or molecular orbitals, or bonding orbitals, however you want to describe that. If you had electrons in these anti-bonding orbitals, that would lead to a higher energy arrangement, which would tend to drive things apart. And that's why, for instance, you can't make helium-2. All right. That's well and good as long as you stick to something really simple like H2. But if we start making molecules with carbon, it turns out the S and P's don't cut it. We have to start mixing and matching them to make what are called hybrid orbitals. Hybrid orbitals are also combinations of atomic orbitals, but they're on the same atom. For instance, if I combine an s orbital and a p orbital, there's 2 different ways to put them together, and I'm going to make 2 different combinations, because remember, if I start with 2 orbitals, I'm going to make 2 orbitals, and I'm going to call them hybrid sp orbitals. So here, if I took a blue p orbital and a red s orbital, here's the blue p, and here's the red s. They both have a nucleus in the middle. The green is the combination. And notice it's got a really big part, it's got a node, and it's got a little negative part. And that's what an sp orbital looks like. I'm going to end up with 2 sp orbitals when I combine an s and a p, and they're at 180 degrees to each other. If I combine 4 orbitals from a carbon, an s, a p, and a p, I'm going to make 4 new orbitals. This should say have a 3 on it. There should be a 3 here. I apologize for that. I'll try and remember to fix that. And those turn out to be 109.5 degrees, a tetrahedral shape, exactly what valence shell electron pair repulsion tells us that we get when we've got 4 bonds. If I combine 3 orbitals, an s, a p, and a p, I'm going to get, as shown in blue here, 3 new hybrid orbitals called sp2s at 120 degrees, a trigonal planar arrangement. But notice I mixed these 3 orbitals, but I left this one alone. I've still got a p orbital that's untouched. And so I end up with this p orbital that's at right angles. Another word for that is orthogonal to the trigonal plane. If I combine an s and a p, I'm going to get 2 new blue. This and this are meant to be separate blue sp orbitals, but now I've got 2 sp orbitals. Or sorry, I've got 2 extra p orbitals. We're going to see this combination anytime we see a linear shape. We're going to see this combination anytime we see a trigonal planar shape, and we're going to see this combination anytime we see a tetrahedral shape. These hybrid orbitals can also be used to make bonds. So in this diagram, I show the overlap between an sp3 hybrid orbital and an s orbital. Imagine a CH bond, like in methane. Methane has sp3 hybridization. And again, when you combine these atomic and hybrid orbitals together, we make molecular orbitals. There's one in phase and one out of phase, and in the case of a CH bond where I had one electron from the carbon and one electron from the hydrogen, we'll end up with electrons in a lower combination, a lower energy arrangement for the combination than for the separate atoms. And we could talk about those combinations. If I have p orbitals that come near each other, they can also interact when they are parallel to each other. So parallel p's make pi's. We call these pi orbitals. And again, there's an in-phase and an out-of-phase combination, and if we have one electron from each carbon, it'll be better to have them together because those electrons will end up at a lower energy arrangement than if they were apart. Putting these into molecules. If I have 2 carbons and 6 hydrogens, if I was to draw a Lewis structure, I'd do something like this. I'd put those together, and I'd start sharing it, I'd end up with bonds. If I want to describe the orbitals, I'd say Vesper tells me that this is a 109.5 tetrahedral shape. That's sp3 hybridization. I've got 4 sp3 orbitals around this carbon and 4 around that carbon. Each of my hydrogens has an s orbital. The combination of an sp3 with an s gives me a sigma bond. When I've got 2 electrons, gives me a sigma it gives me a sigma and sigma star combination. If I have 2 electrons, I fill the sigma combination. That's a sigma bond. So I can also make a sigma bond by combining 2 hybrid orbitals pointing at each other here in the middle. These pictures are other pictures of ethane. These are some of the models. This is the model set that you probably own. This is another brand model set. This is a space filling diagram that shows how much area, or volume I should say, the electrons take up. This is kind of a slice through the molecule where the contours are meant to show the area of highest electron density. In ethene, when you were drawing your Lewis structure, you found that doing simple pairings led to didn't lead you to octets. And so what you had to do was do another pairing, a double bond. A double bond, here we've got 120 degree angles, which is trigonal planar arrangement, sp2 hybridization. So here's a sp2 hybridized carbon with 3 sp2 orbitals and a p. Notice there's sigma bonds to each of the hydrogens and over here. And there's a sigma bond between the 2 carbons, but there's also a pi bond. The p's touching here and here, that's all one pi bond. So a double bond is made up of a sigma and a pi. Part of the pi is up here and part of the pi is down here. Here's some, again, other pictures of ethene models. This is a space filling diagram, and this is kind of showing the electron density contours. Ethine has a triple bond, has a linear shape, which we know due to valence shell electron pair repulsion theory. A linear shape is sp hybridization, and here we see that we've got sigma bonds between the carbons and hydrogens, but the triple bond itself is made up of a sigma, a pi, and another pi, because here we've got 2 pairs of parallel p's. When we drew organic compounds, we saw that there were several ways, and these are just a few of the ways that we drew them. In a condensed formula, this is a real simple way to write, or especially to type, a formula, but it doesn't show us a lot about the structure. You can read it and learn about the structure, but you really have to use a lot of chemical intuition to interpret this. On the other hand, a Lewis structure shows us all of the bonds and all of the valence electrons, all the lone pairs, and it shows us all of the atoms. That's really useful, but a Lewis structure is more tedious to draw, and it sort of lies to us about the shape. It implies that we've got these 90-degree angles when we really don't. So what we usually draw in organic chemistry are these things called line angle structures. We usually draw them mainly because they're the fastest, and because in organic chemistry we know we're talking about carbon, and so we don't have to draw the carbons. So each of these junctions, if it's otherwise unlabeled, so these are labeled, these are oxygens and hydrogen, but each of these, we just assume that's carbon. And so we would fill this in. We would kind of mentally fill in that there's a carbon here, 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 and here. Also, in organic chemistry, we know that carbon is often, very often, bonded to hydrogen. And so each carbon we're going to assume has 4 bonds around it because neutral stable carbons have 4 bonds. We're going to assume that the other bonds, if not shown, must be to hydrogen. So for instance, this carbon has 4 bonds shown. 2 to that oxygen, 1 to that oxygen, and 1 to that carbon. Remember, there's a carbon there. But this carbon only has 2 bonds shown, that one and that one. And so we're just going to assume there's 2 hydrogens here, and 2 here, and 3 here. Notice we do draw hydrogens that aren't attached to carbon. I apologize. So oxygen-hydrogen bonds and like nitrogen-hydrogen bonds should be shown in line angle structures. Notice we also show lone pairs. I'll try and be good and show lone pairs. Sometimes when I'm being quick, I'll not draw them just on the assumption that we all know they're there. But we should try and draw in lone pairs because they're often very important when talking about mechanism. We talked about conformations. These molecules aren't static things. They can take on different shapes. A conformation is like a pose. Like sometimes I stand straight up, sometimes I sit down. But all I'm doing is I'm kind of bending my different parts relative to each other. That's what's going on in conformations. When we have single bonds, different groups can rotate relative to each other. So you might remember talking about staggered and eclipsed conformations. Staggereds are these ones where groups are farther apart and therefore they're lower energy. Eclipsed groups are closer to each other and therefore higher in energy. But notice not all things are created equally. This staggered conformation where the methyls are at 60 degrees to each other, we call that a gauche arrangement, is at a slightly higher energy than this arrangement that puts the methyl groups the anti to each other, 180 degrees from each other. We also talked about the conformations of 6-membered rings. As you probably recall, the most stable arrangement of a 6-membered ring is called a chair conformation, and it makes a difference whether those substituents are in what's called an axial position or an equatorial position. We can flip back and forth from one conformation to another, but the equatorial arrangement of substituents is the lowest energy arrangement. Okay, I show a couple of things on this slide. One I'll get to in a moment is stereocenters, but first I want to note that just because we have the same atoms doesn't mean we have the same molecule. All of these molecules here are C5H10BrCl. But they're not the same molecule. If I look up at these top two, this one here on the right is 1-bromo 4-chloropentane. And this one is 2-bromo 4-chloropentane. I'm not fully naming the stereocenters there. I'll get to that in a moment. Those aren't the same thing. We call these constitutional isomers because they have the same atoms, but they're connected up in a different order. On the other hand, these two molecules, or this pair and this pair, in each of these pairs we have the same atoms and there's the same connectivity. That is a 5-carbon chain with a bromine on position 2 and a chlorine on position 4. That's the same here and here and here. But these aren't the same molecules because of these dashes and wedges. Wedges are things coming towards us and dashes are going away from us. Whenever I've got a carbon with 4 different groups attached, like this one, or 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 this one, this carbon has a chlorine, an implied hydrogen going back, a CH3 here, and this 3-carbon group with a bromine over here. So there's 4 different things attached. That's a stereocenter. This arrangement and this arrangement are not identical to each other. They're mirror images. This one is, it turns out, R, and this one is S. We go back and review naming, but I'm not going to take the time to do that right now. But here I want to compare these two molecules to each other. These two molecules turn out to be mirror image molecules, but not the same thing. This one is, the molecule on the left is 2s4r, 2-bromo-4-chloropentane. The one on the right is 2r4s, 2-bromo-4-chloropentane. Notice in those names, everything's the opposite, because in the mirror, everything's the opposite. Your right hand, when it looks in the mirror, sees a left hand. Your right foot sees a left foot. Your left foot sees a right foot, etc. Mirror image molecules that are not identical to each other are called enantiomers. On the other hand, this pair, we have the same atoms, and they're connected in the same way. Both have a bromine on 2 and a chlorine on 4. Different three-dimensional arrangement, but they're not mirror images, and we call these diastereomers. This one is 2r, 4r, and this one is 2s, 4r. Notice they're not the same, but they're not exactly the opposite. Those are diastereomers. To this point, we've talked about neutral stable molecules, but we also have to understand a little bit about reactive intermediates. Reactive intermediates are atoms that don't either have incomplete octets or they have an imbalance of charge. So, for instance, carbocations and carbanions are charged. Carbocations are positively charged. They've got 3 bonds and 0 lone pairs. Carbanions have 3 bonds and a lone pair. They're negatively charged. We talked a fair amount about those last semester. Especially, we talked most of all about carbocations, and even this semester we'll talk quite a bit about carbocations. These bottom 2 reactive intermediates, radicals and carbenes, we did not talk about much at all last semester. We will talk about radicals somewhat more this semester. Carbenes I'll mention like twice. But these are neutral because a radical starts with 4 for a neutral carbon atom, minus 3 minus 1, that's 0. Carbenes, 4 minus 2 minus 2 is also neutral. Notice these don't have full octets, and so they're reactive species. We'll learn later on about the properties of these. And again, I should mention that carbenes we'll see like twice. And finally, resonance. Let's just come back to resonance because it's an important concept. Resonance helps explain the structure of molecules. It also helps explain their properties. It also helps explain some of their reactivity. There are 6 main types of resonance you'll see in organic chemistry. Several of them involve reactive intermediates adjacent to pi bonds. So a carbocation is essentially an empty space because there's an empty p orbital. This carbon with the positive charge needs extra electrons. Well, right next door, there's this pi bond. If these pi electrons move over here, we'll make a double bond here, but of course this carbon lost electron density, so we get a plus charge here. But the real thing is neither this nor this, but it is an average of the 2. And so we get some average species that's got some amount of positive charge here and some amount here, and it's got electron density spread across these 2. A carbanion adjacent to a pi bond can also be shown as 2 different resonance forms, and the real thing is an average. And the same is true of radicals. We also saw a benzene ring briefly last semester. That is a ring of alternating single and double bonds. And I could put the double bonds here, here, and here, or here, here, and here. And it turns out the real thing actually has those electrons equally distributed around the ring. We'll learn more about aromatic molecules in about a month. Double bonds, polarized double bonds, especially carbon-oxygen double bonds, we'll spend a fair amount of time this semester on functional groups that involve CO double bonds. The key thing to know is this resonance. It's got a mixture of this in with this, which means the carbon end is partially positive and the oxygen end is partially negative. That will explain almost all of the chemistry associated with CO double bonds. And then finally, this last picture is hyperconjugation. hyperconjugation, the only real time that you'll use it is to explain why tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations. We'll also, at one point, I'll refer back to it briefly when I talk about alkyl groups as being slight electron donors. But other than that, hyperconjugation is not something to spend much time thinking about. All right, that's it. That's the structure of organic molecules as you learned it last semester. We're actually not going to learn much more about structure this semester. We'll learn some. But we're going to use these principles of organic structure in our understanding of the reactions that we learned this semester. All right, thanks, and we'll move on in our next section to talk about reactions.